All right, so today we're talking about molecular geometry. Hopefully you remember a little bit of this from last year, but there's going to be a couple things that are added for AP because you're an AP, so why wouldn't we add some more stuff? But starting from the very beginning, why do we even care about shape? Because it helps to determine the polarity of a molecule, right? Based on the shape, you can determine the polarity. Hopefully, you remember about polarity. We will also see a video about that. It also helps determine the reactivity of molecules. If things are shaped a certain way, they will be more reactive than some others. It's very important for biological systems because in biological systems, there are things called enzymes, and enzymes work as catalysts. And how they do this is by interacting with molecules that have a particular shape and turning them so that their reactive parts are close to another molecule that needs to react with it, and they hold them there. And it works great for making chemical reactions. It holds molecules in the right position to react with other molecules, but it will only work with things that have a particular shape. And it's also important for understanding intermolecular forces, which we will see in a video soon. So if you remember this chart, hopefully you remember it fondly. In this class, because it is AP, yes, you will need to know it. Just memorize it. I don't really have a good strategy for memorizing it other than tell you you'll just need to memorize it. And it really is only five base shapes, right? These ones that are kind of here in this line. And then if they have some number of lone pairs around them. So really, it's only five shapes, and then they have some number of lone pairs. So you will need to know that. There will probably be questions about the molecular shape on the test, so just learn it. Okay, going from dot diagram to shape. Hopefully you remember from some previous videos how to draw dot diagrams. I'm not going to go through a complete step-by-step process here because it's in the other videos, but we're going to learn about going from dot diagram to the shape. So let's start with our trusty methane. So we know that the central atom is carbon because that's always the center. Hydrogen's going around it. We could put in our electrons, but I know how many carbon has, I know how many hydrogen has. So we're just going to fill in our single bonds. We'll check for our full octet, which we do have a full octet, right? 4 single bonds, it's 8 electrons. So now, if I draw my hand back up here, we can count the number of bonds or electron domains here, right? So here we have 1, 2, 3, 4 bonds, which are each an electron domain. So you have 1, 2, 3, 4. Pretend that I'm counting on my fingers here. And so then when we figure out that we have 4 electron domains, we look here in the electron domains. And we see we have 4, which means it's going to be one of these 3. We look to see, is any of these electron domains a lone pair? The answer for that is no. And so, with no lone pairs and 4 electron domains, we have a tetrahedral shape. It's as easy as that. Now, if we have, let's say, SF4 as our molecule, right? We know that fluorine is never the center, so we're going to have sulfur in the center, our 4 fluorines around it. We're going to draw in our single bonds, but then sulfur has 6 valence electrons, so we put our lone pair around sulfur. I'm going to count on my fingers again. And we have 4 bonds, so that's 1, 2, 3, 4 electron domains, and then 1 lone pair for a 5th electron domain. So we come over here, number of electron domains, we have 5. So it's going to be one of these here. Now, we look, we have 4 bonds and 1 lone pair. So we look here, 1, 2, 3, 4 bonds, and our 1 lone pair. So we know that this is going to be seesaw. Just like that. Easy enough. Hopefully that illustrates how we figure out the dot diagram shape. We can do one more if we do HCN, right? Like in our previous video, or even if you don't remember it, right? Carbon is going to be the center. We have our 4 and our 5 electrons, right? But there's not a full octet around either nitrogen or carbon. We want to use some electrons to make some extra bonds. So we are going to use 2 electrons from carbon, 2 electrons from nitrogen, and make a triple bond. Now, if you count on your fingers again, looking at carbon, carbon has 1, 2 electron domains, right? Because any bond, single, double, or triple, counts as 1 electron domain. So we have 1 single bond, 1 triple bond. We have 2 electron domains, and in this case, there's only 1 shape for 2 electron domains, and this molecule is linear. Okay, great. Bond angles. So, bond angles, this is what we are going to add to this. Now, your book does a great job of going through this and looking at the diagrams, so you should definitely read 9.1, 9.2, and 9.3. I will go through this here, but take a look at your book. So, linear. If we have our central atom in the middle, hopefully everyone at home, if I am asking what this bond angle is here, a straight line on either side of 1 point, hopefully everyone is shouting, "Brad, it's 180 degrees." And you'd be right. Great job. Now, if we have our trigonal planar here, which is not particularly evenly drawn, but if it was evenly drawn, all of these 3 angles would be the same, and if you split 360 into 3 even angles, I hope you're all now yelling, "It's 120 degrees." Great job. Fantastic. Way to go. Now, tetrahedral, right? Here's the tricky part, because this is in 3 dimensions, right? This is no longer a flat molecule. Now, each of these angles is the same. I will tell you right now it is, but it is not an obvious angle. So I will tell you what the angle here is. It is 109.5 degrees for a tetrahedral shape. Now here's the tricky part. When you have 1 lone pair as one of the places, the angle shrinks. This one is about 106. And then again, if you have 2 lone pairs here as 2 of the spots, it shrinks again to about 104.5. So what's going on here is that these lone pairs, right, they're in their hybridized orbital and they're taking up a bunch of space, right? Electrons do not like to be near each other. And what's happening is, right, this is pushing on all the other bonds that are close to it, right? Because bonds are just electrons. and they're pushing those electrons in the bonds away from the lone pair, and so making the angle smaller. All right, so that is what's going on with those. Then if we look at the other two base shapes, right, our trigonal bipyramidal, we have two different angles, right? Here we have a 90 degree, right, because that's between an upright and something, essentially it's between something on the X and Y axis. And then around the center, right, we can think about it as trigonal planar, which means we've got 120. And then our octahedral, right, this one is going to be all the same angle, and they are all 90 degrees. So those are the bond angles for all of your bond shapes. Again, look in your book because they do a good job of showing what's going on. Symmetry and polarity. I know we talked about this a little bit last year. We can talk about it again. Molecules that are symmetrical are almost always nonpolar. Molecules that are not symmetrical are almost always polar. Symmetrical molecules can be nonpolar even if they contain polar bonds. Shapes that are never symmetrical, right? There are some that are never symmetrical. Bent, trigonal pyramidal, seesaw, T-shape, square pyramidal. And then there are some shapes that can be symmetrical. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, square planar. So these shapes are always symmetrical, right? These ones here in this second one, right? Right here, right here, right here too. Those shapes are always symmetrical when all elements bonded to the central atom are the same. Otherwise, you'll need to use your best judgment. Which means, right, we're going to do some examples. So if we have CH4, right, carbon with 4 H's around it, we look, there's 4 electron domains, which means we're here. None of them are lone pairs, so we have tetrahedral. And tetrahedral being one of the ones that I said can be symmetrical if all of the elements around it are the same, which means this one is nonpolar. Now, if we have CH2, Cl2, right? We have 2 chlorines, we have 2 hydrogens, we have 4 electron domains, none of them are lone pairs, so again, right, we have tetrahedral. Now looking at this, you would be tempted to say probably that that's symmetrical and that that is not polar. However, if we draw our element in its shape and we put Cl's and our H's, you can see now that it is not symmetrical and that it will be polar because we have chlorines here that are more electronegative, right? And we can draw in the direction of the polarity. And in fact, that is how you draw polarity. We would draw our arrow with the little plus here, right, going towards the negative. And this is polar because it is not symmetrical. We will do more practice and examples like this in class, so I will leave it there with those 2 examples for this video. So now some things to remember. The shape of a molecule is determined by the number of electron domains and how many of those domains are lone pairs. So whether or not a molecule is symmetrical can help determine if it's polar or nonpolar, and then molecules can have polar bonds and still be a nonpolar molecule. The prime example of this is carbon dioxide, right? Carbon and oxygen, it's a polar bond, but because the molecule is linear, right? If we draw it linear, it is a nonpolar molecule because it is symmetrical. The polar bonds essentially cancel each other out. Okay, that is it for this video. I will see you in class.